checking. I think it is now in the full screen mode.
Okay.
Great.
Yes. Let's get started. We're very happy to have Rehan here today to tell us something about fluid and P-form duality. It's all yours.
Thank you so much. Hi, everyone. I hope you are doing well. Thank you for your kind invitation. It's a great pleasure for me to give a talk here. Um, Today, I'm going to talk about fluid gauge duality or fluid P-form duality. This is based on a work by my excellent collaborator. Uh, Okay, let's start by with giving a one-sentence summary of the talk. The principal assertion of this talk is as follows. An inviscid fluid in near equilibrium state, when viewed in the Lagrangian picture in B plus 1 spacetime dimension, can be reformulated as a B minus 1 form gauge theory. This is the main statement of this talk. This statement states that a fluid is dual to gauge theory. Please note that all these conditions are necessary to make this duality. The fluid should be dissipationless. It should be in near equilibrium state. And as I will um, explain in more detail, please. Um, is there any question?
Good so far.
Good, good. As I will explain in more detail shortly, I will construct this duality in the Lagrangian picture. Uh, D minus form D minus one form gauge theory is a gauge theory that its corresponding gauge field is a D minus one form field. It has D minus one indices which are totally antisymmetric. This is the main statement of this talk. Let me give two examples. For example, a fluid under these conditions in 2 plus 1 spacetime dimension is dual to Maxwell's theory in the same dimension. As another example, in 3 plus 1 dimension, such a fluid is dual to a two-form gauge theory. Okay. Now, let me present the fluid gauge dictionary. I will construct this dictionary step by step throughout the talk. But this dictionary relates various quantities in both sides of the duality. According to this dictionary, fluid velocity is related to the electric field on the gauge theory side. Fluid density corresponds to magnetic field. Vortices in the fluid side is dual to d minus 2 branes. For example, in 2 plus 1 dimension, vortices are dual to particles, point particles. We call this duality as particle-vortex duality. In 3 plus 1 dimension, vortices are dual to strings. We call this duality string-vortex duality. And in higher dimension, in general case, vortices are dual to B minus 2 branes. Circulation, which represent the power of vortices, are dual to electric charge of D branes on the gauge theory side. Interestingly, the freedom in relabeling of fluid parcels, namely the volume-preserving diffeomorphism on the fluid side, are dual to U1 gauge symmetry on the gauge theory side. The seminal Kelvin circulation theorem is related to Gauss law on the gauge theory side. And finally, I will show that the mass continuity equation is nothing else than the Bianchi identity on the gauge theory side. As I mentioned, I will construct this dictionary and this duality step by step throughout the talk. Okay. But before going on, let me highlight the main idea behind this duality. The cornerstone of this duality is the seminal Kelvin circulation theorem. in the fluid mechanics, which states the power of the vortex are conserved in time. To illustrate this, let's look at the Gauss law in electromagnetism. The Gauss law states, according to the Gauss law, assume we want to compute the total electric charge within a given volume V. To do so, we only need to take a volume integral over electric charge density. Now we remember from the Gauss law, we can rewrite the electric charge density in terms of the divergence of the electric field. Now, by using the divergence theorem, we can invert this integral into a surface integral. The main point that as you can see, the integral of a conserved quantity reduced from 3 dimension to 2 dimension, from a volume integral into a surface integral. The point that I'm going to stress that is that reduction of volume integral is a direct reduction of volume integral into surface integral is a direct consequence of the underlying gauge symmetry. For example, in electromagnetism case, it is a direct consequence of underlying U1 gauge symmetry. Okay. Now let's look at the Kelvin circulation theorem in fluid mechanics. Let me explain this theorem in 2 plus 1 dimension. This theorem states that a quantity which is called circulation is conserved in time. Let me define this quantity. This quantity defined as a surface integral of vorticity. Okay, vorticity is a measure of local rotation in fluid system. More precisely, it is given as the curl of the fluid velocity. Okay. Now, if we put this expression into the integrand, we can take the integral and convert this two-dimensional integral into a line integral. The Kelvin circulation theorem states that this quantity is conserved in time. Again, we encounter the reduction of an integral of a conserved quantity here from 2 dimension into 1 dimension. So this observation, put this observation beside this point. This motivates us. One can guess, one can find this the Kelvin circulation theorem. One can reformulate Kelvin circulation theorem in terms of a gauge uh, gauge gauge theorem. In other words, this motivates us to reformulate an inviscid fluid in 2 plus 1 dimension in terms of a gauge theorem. As Bacall and Susskind showed in 1991, this gauge theory is nothing else than the Maxwell electrodynamics in 2 plus 1 dimension. Please note that this theorem holds only for dissipationless fluids. So we expect this duality holds only for dissipationless. Okay. Let me explain the Kelvin circulation theorem schematically. According to this theorem states take a vortex in the fluid and take a closed curve around the vortex and measure the fluid velocity around the closed curve. Then then you can find a quantity which is conserved in time. We call this quantity the circulation. Okay. The main point about the Kelvin circulation theorem is hold in any space-time dimension in the same form. It is expressed as a line integral in any space-time dimension. Please note that this property is not present in the Gauss law in electromagnetism. For example, in d plus 1 dimension, the Gauss law in electromagnetism states gives the total electric charge as a co-dimension 2 integral, as a d minus 1 dimensional integral, which is explicitly depends on the dimension. But Kelvin circulation theorem in any space-time dimension is expressed as a line integral. Okay, for example, in 3 plus 1 dimension, the Kelvin circulation theorem states take a closed curve around the vortex. This vortex in this dimension is a line, is represented by a line. And this theorem states you can take a closed curve around the vortex and sum them up, and then you can project the fluid velocity along the closed curve and sum them up. Then you can find a quantity which is conserved in time. As I mentioned, the fascinating property of the Kelvin circulation theorem is it holds any space-time dimension uh, in any space-time dimension, and more importantly, it's expressed as a line integral. Let me remember that we usually expect conserved charge to be written as a volume integral, but in the Kelvin circulation theorem, we encounter a line integral. So this observation motivates us to ask, is there any gauge theory to reduce the d-dimensional conserved charge integrals into line integrals or not? Interestingly, the answer is yes, and a d-1 form gauge theory does the job. So this motivates us to reformulate a dissipationless fluid in d plus 1 space-time dimension in terms of a d-1 form gauge theory. To illustrate that a d-1 form gauge theory does the job, please let's look at the Maxwell-like equation of motion in d-1 form gauge theory, which is as follows. Here, F is the d-form field strength, and J stands for the d-1 form current. Okay, this is the analog of the Maxwell equation. Now, because the current is d-1 form field, we can take it to compute the total charge associated with this current. We can take its integral over a codimension d-1, which is equivalent to a two-dimensional surface. In other words, we have this expression. Now, by using the equation of motion, now let's rewrite the current in terms of the field strength using the equation of motion. We can find this expression. Now, by using the Stokes theorem, we can convert this two-dimensional integral into a line integral. So this is a d-1 form gauge theory provides what we want. So again, this motivates us to reformulate an inviscid fluid in d plus 1 dimensions in terms of a d-1 form gauge theory. Okay, I will explicitly construct this theory by starting from an action for a fluid system. Great. After this such a comprehensive introduction, I think it is time to present the outline of my talk. In the first part, I will talk about gauge a fluid system in Lagrangian picture. In the second part, I will reformulate a fluid system in the language of gauge theory. But before going on, let me explain two standard pictures in fluid mechanics. Um, we usually describe the kinematics of fluid system, a fluid mechanical system, into picture, Eulerian and Lagrangian. The Eulerian picture is the picture we usually encounter in a standard course of fluid mechanics. In this picture, we attribute velocity to different points in a space. For example, here we denote the Eulerian velocity, which is a function of x and t. It represents the velocity of a fluid parcel which passes through the point x at time t. Please note that at different times, different particles pass through point x. So we cannot assign this velocity to a specific fluid parcel. In other words, because at different times, different particles pass through the point x. On the other hand, in the Lagrangian picture, which is the natural generalization of the Newton's second law, we consider a fluid system as a collection of as a collection of particles and label these particles and track them along the time. For example, here I have labeled fluid parcel with their initial position y, and here v denotes the Lagrangian velocity, which is a function of y and t. This describes the velocity of a particle at time t. Which particle? That particle was located at point y at initial time. This is the picture that I'm interested in considering a fluid system in the following. Okay. Now let me consider a fluid system. Let's assume we have a collection of non-relativistic particles in d plus 1 space-time dimension. Here L denotes the Lagrangian of the system. The first term is the kinetic term, and the second term is the potential energy. Here I have assumed all particles have the same mass m, and alpha describes the discrete label of the particle. And the second term, as I mentioned, is the potential energy. It depends on the fluid velocity and the position of the it depends on the position of the fluid parcel and their velocities. I'm interested in the continuum limit, so I need to replace the discrete label with a continuous label. I denote the continuous label with y. You can think about y as the initial position of the fluid parcel. So we have two kinds of spaces, X space and Y space. Y space the initial describes the initial position of the fluid parcel, and and X space, which is the real space, and denote the position of the particles at time t. Now let's denote the density of the fluid in the X space with rho and in the Y space with rho zero. From the mass continuity equation, one can find this relation between this density. Here, this term is the Jacobi of the transformation between y and x space. Now let's take the continuum limit of this Lagrangian. One can simply find this result. Here, the first term represents the kinetic term, and the second term stands for the potential energy. Please note that when here the potential energy is expressed as an integral over x space, but here it is expressed as an integral over y space. So one can simply convert this to integral by a Jacobi factor. I absorb this Jacobian in the definition of V. In other words, V is equal to Jacobi factor times U. Okay. Please again note that when we take this continuum limit, we need to take all spatial derivatives of x and x star. But here uh, a first derivative. This is because I have implicitly assumed the interparticle interaction are short range, so I only kept the first derivative. As another point, I only kept a specific combination of first derivatives. This is because I'm going to demand this collection of particles to describe a fluid system. A fluid system is distinguished from other systems, for example, solids, by their enhanced symmetry, namely volume-preserving diffeomorphism, okay? As I explained in the next slide. One can simply check that the constructed action is invariant under the following volume-preserving diffeomorphism. Please note that this diffeomorphism on Y space. The physical meaning of this diffeomorphism is that we demand our system is invariant under relabeling of fluids parcels. Okay. Uh, To show that this action is invariant under volume preserving diffeomorphism, we need to assume the xi's are uh, a collection of scalars under this diffeomorphism. Now let's look at its infinitesimal version. I I have denoted the infinitesimal version with capital Y, and the volume-preserving condition in the infinitesimal version yields that the divergence of y should be zero. Y should be divergence free. When using the Poincare lemma, one can simply locally solve this equation. One can rewrite y as the derivative of an antisymmetric object. Here, lambda is antisymmetric in its indices. One can simply see that this satisfies this equation. Okay. As a final point, let me stress that this volume-preserving diffeomorphism form a non-abelian algebra under the standard uh, Lie bracket. Okay. The volume-preserving diffeomorphism are symmetries of the fluid action in the following sense. The action of the fluid system change under the volume-preserving diffeomorphism up to a total derivative term. Now we have an action and a collection of symmetries. We can go through the standard Noether theorem and construct the corresponding Noether charges. Here I'm going only to present the final result. One can simply compute that the Noether charge associated with volume-preserving diffeomorphism are given as follows. Here P is the canonical momenta, and as I mentioned, Qy is the Noether charge associated with y. We call the integrand of this the Noether charge without y as the Noether momentum charge aspect. It is simple uh, to show that the Noether momentum aspect charge under the Poisson bracket form the following non-abelian algebra. This algebra is equivalent to the Heisenberg algebra. One can simply show that the xi and pi make a Heisenberg algebra, and from that algebra one can simply derive this algebra among the charge aspects. Okay. Here I'm going to show that the Kelvin circulation theorem arises as a consequence of volume-preserving diffeomorphism. To do so, we only need to take the explicit form of the diffeomorphism in the expression of the Noether charge. Uh, to do, one can simply we only need to rewrite y in terms of lambda. If we do so, we find this expression. Now, by an integration by part, we find this result. Please note that this q lambda should be conserved in time for any lambda. So this results the integrand, I mean this factor uh, should be time independent. This is a two form, so we can simply take its integral over a two-dimensional surface as follows. Now, by using the Stokes theorem, we can convert this two-dimensional integral into a line integral. Now, this is an integral over y. One can simply change the integral variable from y to x and find the following expression. Here, uh, this when we rewrite this expression in terms of x, we find this result. This is nothing else than the Kelvin circulation theorem, which is a state that circulation is a constant in time. Okay. Now, from now on, I'm going to 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 reformulate the fluid system, the previously discussed fluid system, in the language of gauge theory. Okay, as I mentioned, I'm going to construct this this duality for only near equilibrium states. So first of all, I need to define the equilibrium state. I define the equilibrium state as the state that the fluid velocity is vanishing. Because the fluid velocity is vanishing, the position of fluid parcels at time t equal to its initial position. I mean x equal to y. Now let's look at the near equilibrium state. So we take x equal to y plus a fluctuation field. I denote the fluctuation with carefully A. Now from the fact that xi's change under the volume-preserving diffeomorphism as a scalar field, one can simply find that this ai's, the fluctuation field, transforms under the following transformation as follows. Please note that this fluctuation field is small with respect to yi. So here we can neglect the second term with respect to the first term. From now on, I'm going to only consider the linear transformation. As you can see, this transformation is reminiscent of the gauge transformation for the gauge field AI. As I will show in more detail shortly, this is the case. Okay. Now let's look at the fluid quantities in the near equilibrium. One can simply show that the fluid density in terms of the fluctuation field is given as follows. And when Please let me mention that from now on I'm going to only consider the potential energy which is only depend on the uh, density on the density. Let me just a second. Here, the potential energy is a function of x dot, and rho. From now on, I'm going to only consider the dependence of V on the second argument and forget about its first two arguments. One can simply generalize this computation. Sorry. Okay. By this assumption, one can simply find that the potential energy in near equilibrium state is given as follows. Here V0 is a constant, and also A is another constant, which arises from the expansion. Now we can rewrite the fluid Lagrangian in terms of the fluctuation field AI. Here the first term arises from the kinetic theorem, and the second term obviously arises from the potential energy. To make the form of the Lagrangian more familiar, let me introduce the Hodge dual of AI. AI is a one form. Uh, instead of AI, I'm going to work with its dual, which is a d minus one form. If we rewrite the Lagrangian in terms of the Hodge dual field, we can find this result. Again, to make this Lagrangian more familiar, let me introduce the field strength associated with this d minus one form field, which is expressed as the exterior derivative of the A field. If we do so, we can simply find the following result. This action describes the near equilibrium state. In other words, this action is an effective action for near equilibrium states. This is a d minus one form gauge theory because the corresponding gauge field is a d minus one form. For example, in 2 plus 1 dimension, it is nothing else than the Maxwell theory. Obviously, this action is invariant under the following U1 gauge transformation. Here, lambda is an arbitrary d minus 2 form. It is the Hodge dual of a small lambda. Okay, this is a part of the main result of this talk. Now I'm ready to introduce a part of Floyd P-form dictionary. According to this dictionary, fluid velocity is related to the temporal component of the field strength, and fluid density is related to the spatial component of the field strength. To, uh, to, to, to derive this dictionary, it is sufficient to, for example, to look at this expression. Here, rho is given in terms of the divergence of AI. If we rewrite this equation in terms of the Hodge dual of A, and again rewrite it in terms of the field strength, one can simply show that rho is given in terms of the spatial component of the field strength. And to find the dictionary for fluid velocity, let's look at this equation. If we take the time derivative from both sides of this equation, we find that x dot equal to a dot. Then now if we rewrite this equation in terms of the field strength, one can simply show that fluid velocity is related uh, to the temporal component of the field strength in the temporal case. Okay. So, in summary, fluid velocity is related to the electric field, and fluid density corresponds to magnetic field, the spatial, which is equivalent to the spatial component of the field. Okay. To make the following analysis more simpler, let's choose the index-free notation. Here, F is the field strength, which is a D form. Star of F is associated Hodge dual, which is a bond form. So the integrand is a top form. This action obviously is invariant under the following gauge transformation. One can simply find the following equation as the equation of motion associated with this action, which in index notation is nothing else than that divergence of field strength should be zero. Let's let's split this equation in temporal and spatial parts. Then we find that the first equation is nothing else than the Gauss law. It states that divergence of electric field should be zero. And the second term is the analog of the Ampere-Maxwell equation. If we rewrite the first equation in terms of the fluid variables, we find that the curl of the fluid velocity should be zero. And and when we rewrite the second equation in terms of fluid variable, we find that this equation is a dynamical equation which which gives the dynamics of the fluid system in the Lagrangian picture. In other words, this equation is the Lagrangian counterpart of the Euler equation in the Eulerian picture. Okay. Now here I'm going to consider the rule of the source in the rule of the source in this duality. One can simply generalize this equation by adding the source term on the right hand side. Here J is represent a D minus one form field which serves as an external source for this theory. Okay. Please note that charged objects in P plus one form gauge theories are known as p-branes. In our case, we deal with D minus one form gauge theories, so the charged objects are D minus two branes. For example, in 2 plus 1 dimensions, the charged objects are point particles, while in 3 plus 1 spacetime dimension they are strings. Now the main question is, what is the dual of these branes and what is the dual of this source in the fluid on the fluid side? Okay, the answer is very simple. To answer, please let's look at this equation. If we add the source in the theory, then the right-hand side of this equation becomes non-zero. If we rewrite this equation, as I mentioned, if we rewrite this equation in terms of fluid variables, we find that the curl of fluid velocity should be non-zero, should be equal to something. So this simply shows that the D minus two branes are dual to vortices in the gauge theories on the fluid side, because when we add source, K, we find that curl of fluid velocity should be non-zero. This, in other words, the right hand side shows the vortices for the fluid system. So this simply shows that charged objects, I mean d minus 2 branes on gauge theory side, are dual to vortices on the fluid side. We refer to this duality as brane vortex duality. To to make more explicit, let's look at a 2 plus 1 dimensional case. Let's look at the Gauss law in 2 plus 1 dimensional electromagnetism. The Gauss law states take for example a point particle. Here I denoted it with a red point. Then choose in 2 plus 1, choose a closed curve and measure the flux of the electric fields from this closed curve. Then you can simply find the total electric charge between the closed curve. Now let's look at the Kelvin circulation theorem in 2 plus 1. The Kelvin circulation theorem states take a vortex and again take a closed curve and measure the fluid velocity around the curve. Then you can find a quantity which is conserved in time. This quantity represents the power of the vortex. You can simply see that these two pictures are dual. In other words, Gauss' law in electromagnetism is dual to Kelvin's circulation theorem, and and the total electric charge is dual to the circulation, which represents the power of the vortex. Okay. Here I'm going to show that Gauss' law. I'm going to show that why 3 plus 1 dimensional electromagnetism is not dual to a fluid system in 2 plus 1 dimension. I'm going to show that why they are not dual to each other. Please note that in 3 plus 1 dimensional electromagnetism, charged objects are point particles, and the Gauss law is expressed as a codimension to integral, which in 3 plus 1 dimension is equivalent to a two-dimensional integral. Why in the Kelvin circulation theorem in 3 plus 1 dimension, uh, our vortices are lines, not points. And Kelvin circulation theorem states take a closed curve and measure the fluid velocity around the curve. So this simply shows that why 3 plus 1 dimensional electromagnetism is not dual to 3 plus 1 dimensional fluid system. To construct a dual for 3 plus 1 dimensional fluid system, we need a gauge theory which its charged object is a string, not a point. As I previously mentioned, a two-form gauge theory does the job. Great. Now I'm going to show that the Bianchi identity is nothing else than the mass continuity equation. Let's look at the Bianchi identity. Bianchi identity states the exterior derivative of the field strength should be zero. Let's look, for example, in 2 plus 1 dimension, its explicit form as follows. Here, P is the magnetic field and E is the electric field. In 3 plus 1 dimensions, we have a similar expression. Now remember our dictionary. According to our dictionary, the magnetic field is related to the fluid density, and the electric field corresponds to fluid velocity. If we rewrite this equation in terms of fluid variables, one can simply find this equation. This equation is nothing else than the mass continuity equation. So mass continuity equation corresponds to Bianchi identity on the gauge theory side. Okay. In the following slides, I'm going to consider the symmetries and conserved charges associated with D-1 form gauge theory. Please note that we have an action and a collection of symmetries, so one can simply ask what is the corresponding noether charge. Here, as I meant, I'm going only mention the final reason. It is not hard to show that the noether current associated with gauge symmetries is as follows. Here J is the default, star of F is the Hodge-Dual of F, and lambda represents uh, denotes the gauge parameter. One can simply check that this noether current is conserved. It is very simple. When the exterior derivative acts in first term, it vanishes because of the equation of motion. When it acts on the second term, it vanishes because of the Bianchi identity. Okay? So from the Poincare lemma, one can simply rewrite the noether current in terms of a d minus one form field, which its explicit form is as follows. Now we are ready to compute the noether charge. We only need to take the codimension one integral of the noether current, and from the fact that J is a total derivative, one can simply rewrite this as a codimension two integral, which its explicit form is as follows. Now, here I'm going to consider global symmetries. Global symmetries are defined as symmetries, the symmetries that do not change the gauge field. So, by definition, they should be closed form. For example, for a specific gauge global symmetry, let's look at this parameter. Here, sigma d minus 2 denotes the d minus 2 dimensional hypersurface, and delta of sigma denotes states that we should take all coordinates on this surface equal to 0, and epsilon denotes the volume form on the volume form volume form on the sea. Okay? If we put this gauge parameter in the charge expression, one can simply find this result. Please note that the charge integral is a b minus 1 integral. Because of this delta, one can convert this integral into a line integral. If we rewrite this expression in terms of the float variables, we find that uh, this charge is nothing else than the circulation. So, this result offers the conservation of this quantity is nothing else than the Kelvin circulation theorem. So this result offers us a reinterpretation of the Kelvin circulation theorem through the lens of the Noether's theorem and conserved charge on the gauge theory side. Okay. Let's look at the Noether current here. Motivated by this expression for the Noether current, we can define a tower of conserved currents as follows. Here, indices denote the rank of the corresponding rank of the form field. For example, here J n plus 2 is an n plus 2 form. Here n goes from 0 to d minus 1. One can simply show that this tower of conserved charge for any n is are conserved on shell. It is very simple. When the acts on a star of f, it becomes 0 by equation of motion, and this expression is identically 0. By using by using the Poincare lemma, one can rewrite these currents in terms of n plus 1 form field, which is its explicit form are as follows. Then we can simply find we have the Noether current, we can simply find the Noether charge by taking the integral over the Noether current and find the following expression uh, for the tower of conserved charge. Here we have a tower of noether charge for any n. If sorry, n should be n goes from 0 to d minus 1. For example, when we take n equal to 0 and when we take lambda equal to 1, we find that the circulation is the consumption. But please note that here we have infinitely many conserved quantities. It is interesting to consider its physical interpretation and application. Okay, let me pause here and give once again one sentence summary of the talk. In this talk, we show that an inviscid fluid in a near equilibrium state in the Lagrangian picture in d plus 1 dimension is dual to a d minus 1 form gauge theory. We constructed the fluid gauge dictionary uh, which states that fluid velocity and density corresponds to electric field and magnetic field correspondingly, and uh, are vortices are dual to d minus 2 branes. The power of the vortices, I mean circulation, uh, are related to electric charge of d minus 2 branes. Volume preserving diffeomorphism on fluid side corresponds to U1 gauge symmetry. And finally, Kelvin circulation theorem and mass continuity equations are related to Gauss law and Bianchi identity, respectively. Uh, let me highlight some interesting direction for future studies. One a natural question is how we can reformulate, how we can construct the dual fluid system in the Eulerian picture instead of the Lagrangian picture. Another interesting question is how we can add the effects of the dissipation. It is a challenging problem because when we turn on the dissipation effects, we do not have the Kelvin circulation theory. Another interesting question is what is the implication of this gauge theory formulation? We constructed infinitely many conserved charge, but we we did not consider its physical meaning and interpretation. We only considered a very small part of uh, surface charges, uh, which uh, which was related to Kelvin, which is related to the circulation. As another interesting uh, question is, we know that we have IR triangle for gauge theories, which relates different concepts at IR in IR limit. This triangle, these three corners are asymptotic symmetries, uh, memory effects, and soft theorems. Here we presented a gauge theory description for fluid systems, so one can ask what is the fluid IR triangle. And finally, consider we only consider a fluid system in its near equilibrium. So, another natural question is how can we generalize this situation? One may expect to consider a fluid system in general case. We should the corresponding the dual gauge theory should be an abelian case. Okay, let me stop here. Thank you so much.
Thank you. That was a nice talk. I remember when your paper came out, I thought it looked very interesting, and I figured it'd be nice to have you give a talk to help me better understand what you were describing. Yeah, that's a nice little picture.
Thank you so much. Thank you so much.
Any questions?
Sure, sure. Let me
Yeah, I have
Sorry, please.
yeah, I have one question. So there is a alternative formulation for purely the generalized Maxwell theory, as you write like this P-form gauge theory, as a one-dimensional higher BF theory. Have you thought about also use that
Wait.
formula to talk about some topological structure of the distribution of the charge of this fluid dynamics, etc.?
It's a great question. Please let me mention that when we formulate the fluid system in the Eulerian picture, we need to add BF terms into the action. For example, in 2 plus 1 dimensional case, we need to add the Chern-Simon term, and in higher dimensions, for example, in 4 space-time dimensions, we need to add uh, BF BF terms, which are topological terms. It's an interesting question. Yeah, but at least in near equilibrium, uh, when we consider the effective action for near equilibrium state, we do not need these terms. But as I mentioned, they appear in the Eulerian picture. Yes.
Yeah, I see. Thanks.
Thank you for your question.
And if no, let's thank the speaker again.
Thank you so much for your kind invitation.
It's a nice talk.
Thanks for giving a nice talk.
Yeah, I guess it's quite late our time. So
Yeah.
I guess we will.
Yes.
Yeah. Thank you. Thank you for the talk.
Yeah, thanks again.
Here is mid-time.
Okay. See you.
Bye. Bye.
Bye.